Hello, everybody. I'm Eric Basis. I'm Kalray CEO. Very glad to present our company, to present our product, and also to talk about our industry today. My German is very weak and long time ago in university, but there is one word I understood, which was noch einmal online. So yes, unfortunately, we are not one time again online, and I hope that next time we will have the chance to meet face to face. As you may see, now I will present the company. We based in Grenoble, so in France, not far away from Germany. And so we are very glad to present to our German friends today what we do, and hopefully to continue a great collaboration we have between our two countries. Sylvie, if you want to share the screen and share the first slide. Okay, so today we're going to discuss about new technologies that will have, we believe, a huge impact in the storage market. And more specifically, we will talk about NVMe, NVMe-oF fabric, and DPUs. And we would like to present you with a new product that we announced a couple of weeks ago called the Flashbox, which is actually leveraging these three words, NVMe, NVMe-oF fabric, and DPUs. Next slide, please. So very rapidly, just to introduce who is attending on our side, starting by presenting myself. So I'm Eric Basis. I spent about 25 years in the semiconductor industry, being in Texas Instruments, designing chip for mobile phones, providing software for mobile phones, and then for the last 10 years now, working in the domain of data centers to provide accelerated solutions. It's very exciting to be in this industry, and I'm very pleased to be here today and present what we've done for the last 10 years. Next one, Sébastien.
Hello, so I'm Sébastien Leduc, Software Engineering Director at Kalray. Similar to Eric, I spent most of my career in the semiconductor industry at ST Microelectronics, where I spent almost 20 years working on different topics like audio, set-top boxes, mobile phone chips, and so on. And now I'm very happy to have joined Kalray and address this new market for me at least, which is storage.
Next one, Loic.
Yeah, thank you. So hello everybody. So my name is Loic Hamon. I'm VP Corporate Development Strategic Marketing at Kalray. I joined the company 4 years ago, and as Eric and Sébastien, I spent all my career in the semiconductor, starting with Texas Instruments wireless and moving to a French startup that co-invented the near-field communication technology called Inside. So now I'm glad to be at Kalray with the exciting market that we're addressing.
Thank you, Loic. And Rémi?
Hello, my name is Rémi Goguet. I'm in charge of the software architecture for data center product in Kalray. I spent most of my career in the semiconductor industry, and more precisely in embedded software coming from voice over IP and packet processing and virtualization technologies.
Thank you, Rémi. Okay, so let's maybe go through the agenda. So what we prepared for you today is basically I will present a high-level overview of Kalray for those who do not know the company. Should be a short one, so we've got time for going into the details. And then we will run a video showing the product that we call a Flashbox, so that you can see what we mean and what is this product. Then we've got a business corner. Loic will say a word about the market we address, and then Sébastien will use two use cases to explain how the Flashbox can bring value with very specific use cases. I will say a word about the business models, price, how we sell the Flashbox and our products, and Sébastien will explain the roadmap. And then we have a technical corner. We will really go into the details of the technical implementation for the Flashbox, for the DPU, which is the heart of the value and the heart of the Flashbox. So this is a data processor unit. And then we will introduce the K200LP card, which is, of course, leveraging the DPU, and the open software environment that we provide to our customers, the SDK that we call the Access Core storage solution. And hopefully we will have time for conclusion and call for action. But of course, as we all know, it should be a very open discussion. So do not hesitate through these sessions to ask any question. We'll be very happy to answer. so either directly by the presenter or on the chat. Okay, so let me give a very rapid overview of who Kalray is and what we do. So Kalray is a semiconductor company. We are a spin-off of a very large, well-known European lab called CEA. And actually, the Kalray has been created about 12 years ago. And the idea of Kalray has been to design a new type of processor, a new architecture, which fits the needs to crunch and manage a huge flow of data as fast as possible in real time. So I would tend to say that Kalray really is one of the pioneers of what is called now DPU. So this term now is getting mainstream. 10 years ago, it was a very, very unique and very visionary. But we are one of the more mature companies providing what we call DPU today on the market. And so the usage of DPU, you will see it will really be at the heart of many, many industries in the futures. But we've been focusing on storage since the last 3 years now, because we've seen that with the introduction of new technologies like NVMe and NVMe SSDs, the storage industry required this type of processor to manipulate very, very, very efficiently the huge amount of data that can be now used with this new technology like NVMe. Just a word about the company. So we are about 100 people based mainly in France. We've got offices in US, Japan, and some partners worldwide. We are precisely one of the leading deep tech company in France and Europe. We raised more than 100 million euros so far. We've got very well-known institutional investors, including companies like NXP. NXP is the largest semiconductor provider in the automotive space in the world. And we are a listed company. So the company is listed on Euronext. It's a public company. We listed the company about 2 years ago. So I see one question was about Renault, why Renault and car makers are very interested in this type of technology. For very, very simple reasons. As you realize that this processor, the technology we developed is focused on data crunching, very fast data crunching. And this technology you can apply, as you will see today, in data center space, but also in edge computing space. And of course, next generation of car are very, very demanding for this type of technology. Next one. So and that's basically the goal of this slide, is just to explain, okay, what type of market we address. So basically, we've got two main markets for the technology and the products we have developed. The first one is the data center and 5G edge data center market, okay? And usually what we provide on this market, what they offer is either acceleration cards, so PCI cards or modules you plug into servers to accelerate the most demanding workloads like storage, networking, but also compute and AI workloads. And it happens that we also provide to this data center market complete appliance. So we took the decision to provide, you will see a storage appliance so that our customers, they can very, very easily leverage our technology. And then the second market is about AI and edge computing. This is a much longer term market, sales cycle are much longer. It includes aerospace, it includes automotive, it includes industry 4.0. And we've got a certain number of very, very interesting projects here, but with a product launch, which are of course later than what you can see with data centers, since we have product today available for data centers.
I have a question here from Hartmut.
Okay.
Said, why invested Renault in your company? I'm assuming why did Renault invest in your company is the question.
So I believe I tried to answer just before because I've seen indeed the question in the chat. And so what I was explaining is that the type of technology we have developed is both very relevant for data centers and for storage, but it's also extremely relevant for edge computing and for automotive. Okay, why? Because for example, when next generation of cars, you need more and more computing capabilities and also the capability to integrate on the same chip a lot of functions. And that's the reason why we're working today with car makers and we have shareholders as Renault. Okay.
Thank you.
And that's actually what is explained here in this slide. So I will go very, very rapidly, but just to emphasize that these new type of processors, once again, some in the industry call them DPU, others are using different terminology. DPU, I think it's very relevant. It's really data processor unit. And we'll come back on why they are different. And this is really the point of this presentation here on this slide, is to explain that in the processor industry, actually, you had, of course, processor design for a computer for servers, an x86, or of course, the famous architecture for processing data centers. You have also a new generation which appeared in the 90s, focusing on smartphones, and this, of course, are at the basis of ARM success. And ARM now is also a very interesting alternative to x86 on the data centers. And then what you can see today, and that's the reason why there is more and more momentum about a new type of processor called intelligent processors, or that DPU. You need a completely different type of processor to complement the other one and to be in charge of very efficiently managing intensive workloads. And this type of DPUs are applicable for a wide set of industries, going from data center, storage, autonomous car, but also going to 5G or Industry 4.0. Okay, next one, please. Okay, so coming on what we offer on the data centers and what is very unique with Kalray technology. So basically, as I mentioned to you, our offering is and our core offering is based on acceleration cards. Okay, so we've got PCI acceleration cards, and we will go into the details of the card we designed especially for the storage industry, which is called the K200LP. But really, the technology itself is capable of offloading a huge amount of different type of algorithms that are usually deployed in data center. It goes through storage algorithm to security networking algorithm, as well as edge computing, HPC type of algorithms. All these algorithms actually can very efficiently be offloaded by our technology and our card, and bringing huge value in terms of performance and also in terms of power consumption. And we will show you an example of usage of this card with a flashbox, a very, very concrete example. Next slide, please, Sylvie. And here we are. So this is really the core of our offering today. This is called the K200LP. This is an acceleration card. And it's really a superb alternative to a SmartNIC or FPGA card. And we will try to explain to you what are the key advantages of this card on these DPUs. Okay. And this is really what we want to present today, because we believe the best way to show the value of the technology is really to present a concrete product which is used by our customers. So this product has been launched a couple of months ago. It's called a Flashbox, and it is a SSD disaggregated storage appliance. And the key, you will see the key value of this offering is that it brings a great value in terms of IOPs per dollar. It can be both completely turnkey but fully open. So we provide an SDK so that our customers, our partners, they can actually bring their own software by themselves, their own data services. And it's fully scalable with a very interesting TCO. But let me now run and ask Sylvie to run the video, so that you can have a better idea of what we mean by DPU usage and with Flashbox.
Hi, I'm Samuel Jones, a software development manager on Kalray's data center team. And today I'm proud to present our MPPA DPU, our mini-core processor, as well as our brand new K200LP low-profile board, and Kalray Flashbox, our new NVMe-oF flash array, both integrating our MPPA DPU. So, let's get started with the processor. So this is our MPPA3. That's 10 years of R&D, 80 cores, fully programmable in C, low power, as low as 30 watts in operation. It includes fully integrated high-speed interfaces like 200 gigabit Ethernet, PCI Gen 4, DDR4, and it's ready to crunch data as an acceleration card. And here you go. This is our brand new K200LP card, ready for storage, edge computing, security, and networking. It's very flexible, programmable, and provides data services without any x86. It includes high-speed interfaces such as PCI Gen 4, 2x 100 gigabit Ethernet, DDR4, and it can deliver more than 2 mega IOPs, 12 gigabytes a second per card, and sustain 30 to 50 microsecond latency. And this is Kalray's Flashbox, our NVMe-oF flash array. Now let me remove a drive from the front. This is a hot swappable format, and this really is an example of a new generation of all-flash array powered by our acceleration card. Let's take a look at the back. This is a fully resilient design. We have 2 I/O modules and 2 power supplies, ensuring operation even in the event of a failure. As you can see, it is very easy to remove a power supply, and one can provide enough power for the whole of the chassis at full speed, full IOPs. So this is a fully resilient design. Now let's take a look at the I/O module. You can see here 3 PCI slots, and on the left side, 1 card has already been inserted. Each I/O module is managed by a BMC, so we can have easy management from the outside. So let's remove one of these I/O modules and see what's inside. They're very easy to slide out, very easy for maintenance. The cover is simple to remove. And let's take a look. On the inside, we have plenty of room so we can fit the various components. At the back, we have the connectivity to the PCI fabric inside the chassis. In the middle, we have the controller to make sure that we can collect sensors activity. And here at the front, we have 3 PCI slots so that we can insert Kalray's acceleration cards. So let's insert those cards now. It's interesting to see that in this new generation of chassis, we can accommodate scale-out. 1 to 3 cards per I/O module. That makes 2 to 6 cards for the whole chassis. These DPUs are ensuring high resiliency, so there is no problem accessing data. We have full access to data all the time, and they provide storage services without the help of any x86. This is our Kalray Flashbox, built in partnership with Viking, a Sanmina company. Flashbox is highly available, runs without any x86, with a great list of storage services, all powered by our Kalray DPU. Kalray Flashbox comes with a composer tool that allows you to manage information such as health, performance, capacities, configuration from a series of Kalray Flashboxes. And they're all powered by Kalray K200 LP acceleration cards. Kalray Flashbox offers a unique solution with the best performance, 12 mega IOPS, scalability from 2 to 6 cards and up to 24 SSDs, high-speed interfaces with 2 times 100 gigabit Ethernet, low latency as low as 20 microseconds latency, and low power consumption with only 30 watts per card. Kalray Flashbox offers the best performance per watt and per dollar on the market.
So this was very, rapid introduction of our Flashbox, and I'm sure you will have many questions, but I would like, first, I think we've got a short survey.
But there we go. Everyone has answered now. So I'm going to end the poll and share the results.
Okay.
So, Eric, which one is correct?
Well, I think, all of them are interesting. So what we see in this server is that we are really, starting seeing a largely adoption of NVMe. So some of you believe it's already there, right? Otherwise, it will be very, very soon. So I think that's a very good, a summary of what the industry sees. That there are some early adopter moving maybe faster than over, but that these technologies will happen. And what is very interesting is that you see that we have a 0% never. So I think we are convinced that it will happen either right now or in the next 2 to 3 years. So it sounds good. I agree with this type of feedback actually. Okay, so maybe it's a good transition to go to the next slide. So very rapidly, we would like to share with you our vision in terms of market. So Loic, do you want to take the floor?
Yeah, sure. So I think this is very much aligned with what I'm going to share in terms of market trends. So definitely, this is actually the way Omdia. So I don't know if you know Omdia, but Omdia is like the new name for Informa, Ovum, and the EHS market. So they the big analyst company. So this is the way they see the evolution of the data center servers and the need to have part of the processing that is outsourced to a coprocessor. And this shows as well the different type of coprocessor that they are seeing moving forward. So this is a data center view, centric view. And what we see here, obviously, is that more and more, the host processor most probably it's a x86 type of architecture, is going to outsource part of the processing to a coprocessor and an acceleration card. And that's precisely the market we are in. So definitely on the green here, which is others. So you heard about FPGAs and GPUs. So there is more and more processor that will pop up and outsource a part of the x86. And as we said already, the reason for that is definitely for performances per watt and per dollars. Those kind of processors are better to provide the competitive solutions. So this is for data centers. This is specifically true as well for edge computing. So if we go to the next slide, so we are trying to see this kind of trends as well on the storage, on the NIC, and on the telecom market. So if we take the storage in particular, x86 needs some help to outsource part of the storage services, and typically either on the server side or moving to the server storage appliance. So what you see here is definitely the numbers are really growing in terms of array or in terms of server expansion. If we enlarge a little bit the debate, moving to the smart NIC, this is exactly what we are seeing as well. There is a lot of function, for example, the virtualized networking function that definitely are better in terms of performance per watt and per dollar if they run on external acceleration cards. And this is definitely a market that is exploding. Last example on this slide is the telecom market. So you know that the telecom is going through a revolution with the 5G, and there is need for more and more compute and storage and radio acceleration close to where the data are generated, close to the antenna. And one of the important trends for the 5G is this open RAN, so open radio access network revolution, which is going to be predominant versus traditional RAN in the future. And those open RAN need as well acceleration. And they are doing better acceleration that you can do on a x86. So next slide, we are back to the storage, and this is where Omdia is seeing the storage going. So this is all kind of storage appliances that you can see on the market. The one that are really important for us are the one that are mentioned here in blue, like performance optimized. So this is all NVMe. All the rest are SAS storage appliance. And what you see here is definitely this is probably the growing the market. I mean, the segment that is growing the most importantly. And as Eric said at the beginning of the intro of this presentation, and this is something that we're going to go into the details right now, is those type of performance optimized storage appliance need really DPUs, so they are manipulating a lot of data, and they need those data processing units to be really efficient in terms of performance per cost and per dollar and per watt. So last slide is okay, where you are going to find those appliances, and so definitely on the HPC where there is a lot of data that need to be manipulated, AI, deep learning, financial services, media, lab science. But I think we are going to go into the details and show some use cases associated. So if you have questions, we can move to the next section.
Thank you, Loic. So maybe let's go to two concrete use cases, and I will let Sebastian go through these use cases. Sebastian?
Sorry, I forgot to unmute. I think there is a quick video. Maybe Sylvie, it's time to share it. Thank you. Thank you, Sylvie. So as you have seen in this short video, the first use case is about disaggregation of local SSDs. So basically, the challenges that people usually have is when running data-intensive application on-premise, they need to have some internal drives, SSD drives inside the compute nodes. And basically, this has some drawbacks that we can really remove thanks to Kalray Flashbox solution, which will really help in having a large-scale unified pool of SSDs instead of having local SSDs. This will really allow to decrease the total cost of ownership. So maybe next slide, Sylvie. I think there is some diagram explaining the use case. So basically, normally, what you have today for data-intensive applications is that people will have some local drives, local NVMe drives inside the compute nodes. Whereas with Kalray Flashbox, basically you can remove those local drives and replace them by a Kalray Flashbox, which will expose a unified storage pool that is shared between all the compute nodes in the data center. And this allows to really optimize the full TCO, because you no longer need to over-provision your local storage. You can really have, thanks to Kalray Flashbox, a pool of storage that is dimensioned more as the sum of the needs instead of the max local need. And all that retaining the performances and latency that you have with local drives, thanks to the NVMe over Fabric technology. Next slide. Yeah, so let's switch to a second use case, which is more about accelerating AI training thanks to our Flashbox product. Thank you, Sylvie. So here, as you have seen in this short video, the use case is about artificial intelligence and machine learning acceleration. I would say even to widen it even further, it's basically also addressing HPC use cases where there are massive amounts of data that are required for training in case of AI, or just for HPC, it's usually the same. So thanks to our Flashbox product, again, we are able to offer to replace the usual approach with a large-scale unified pool, still retaining the performances. And this allows again to decrease the full TCO of the solution. Next slide, Sylvie, please. Thank you. So on the left-hand side of the slide, you see the current situation where you have compute nodes on the left side that will access to some parallel file system, which is exposed by some storage nodes. Each storage node usually has some local SSDs within the storage node to expose basically the parallel file system data. And thanks to our Kalray Flashbox, we can really replace the backend storage of the storage nodes by our Flashbox, which in that case really acts as a block backend storage. And thanks to that, we again allow the we again allow to lower the full TCO of the solution, because we have a unified pool of storage instead of having storage within the nodes, basically.
Okay, thank you, Sebastian. Thank you. So I would like to spend a couple of minutes about the business model of Flashbox If you can go to next slide, Silly, thank you. Because I think, so we will go into the technology itself, into how our DPU is innovative, what kind of technology advantage it brings. But I believe also the business model we offer today in the industry is pretty unique, and it's a huge differentiator. So what is this business model? Basically, as you've been presented, we today offer on the market directly from Kalray or through our partners, reseller, integrator, Kalray Flashbox, which is a complete turnkey NVMe fabric storage appliance. But we also allow different users and business model. The one being what we call the build you own storage appliance, which means that if you got your own chassis, okay, so you can use your own chassis or select the chassis that you prefer, and then you can use our cards and build your own actually storage appliance, which is, I believe, extremely interesting for the following reason: is that today, if you look at what is available on the market, there are mainly two main approaches. Either you purchase an expensive kind of black box solutions coming from the large companies like NetApp, IBM, Dell, with a large set of service and support. Okay, but these solutions are pretty expensive, very, very difficult to customize. Either you decide to build your own by trying to leverage existing x86 servers, taking some open source software, some cards, and then you have to develop the complete solution by yourself. Okay, so here our approach is really to provide, I would tend to say, the benefits of both worlds, in the sense that you can build your own solution. You have a full openness. You can really customize it. You will see that the software environment is SPDK based, so completely standard, open. At the same time, you've got something which is fully validated that you can actually use as a turnkey solution. So really the point is to provide the advantage of both turnkey solutions, very efficient, and fully open solution. It happens in some cases, some of our customers, they also want to use the card just as an accelerator to their current solution. So this is always and also possible. So typically our customers, our partners, they may have their own existing storage servers, NVMe storage servers, and then they can use our acceleration card as a way to offload the NVMe storage data services very easily to our card. Okay, example, give you a couple of examples. For example, is a SAF storage node. If you want to offload a lot of the demanding processing for data services, you can offload these services on our card, and it's fully software transparent for the complete system because the card itself is exposed, as you will see, as the NVMe device. Okay, so there again, we will go into the detail of the technology and how we differentiate. But I wanted to assist today on something which is also very unique with Flashbox, which is the innovation in terms of business model. Next slide. So it's about the roadmap. Sebastian, do you want to introduce our roadmap?
Yeah. So the first software release we made was back in September. So it was called ACS 4.6, so which is Access Core Storage version 4.6. So it was released in September. It features support for NVMe over Fabric in TCP transport mode. It supports various ways of exposing the NVMe drives. So basically we support a pass-through mode, which is the most performance efficient mode, where the drives are really directly exposed to the initiator. But we also support some more advanced ways of exposing the NVMe SSDs. We can, for example, expose them with logical volumes, which offer scene provisioning support in ACS 4.6 release. And in this release, the storage management is basically done using a CLI interface. Then we are almost ready to deliver ACS 4.7, which is planned December 15th 2021. This release will add clone support and snapshot support to our logical volume management. We will start our delivery of supporting more advanced storage services. So the first one that will be supported in ACS 4.7 will be RAID 0 support, which allows to increase the performances in case of logical volumes. In terms of management, it will support both system management and storage management through a command line interface. And it is also supported as integrated into different orchestrator solutions like Kubernetes, OpenStack, OpenShift, and OpenNebula, thanks to our integration into Linbit's LinStore offer. So I don't know if you are aware of Linbit, which is a German company. So we have an integration into their LinStore product. And since LinStore offers integration into all the listed orchestrators that I have on the slide, basically by supporting LinStore, we support all of those orchestrators. Then the next version will be ACS 4.8 in March 2022. This will be a major feature in terms of storage service support. Basically, it will be the first version that offers resiliency of data thanks to RAID 10 support. And also it will support high availability thanks to our dual IO module and dual ported disk that the Flashbox supports. So basically, we will be able to sustain up to one disk failure and also be resilient to card failures thanks to the high availability. ACS 4.8 will also have a web UI for system management, and we will have VMware support. So as you know, VMware is now supporting NVMe TCP initiator functionality. And we are currently working on certifying our Flashbox product with VMware so that we are part of the VMware compatibility list, basically. And then in July, ACS 4.9 will introduce RAID 6 support, which will allow us to sustain up to 2 drive failures. Also, it will increase a lot the storage efficiency because depending on how many disks, let's say, what RAID 6 configuration you will choose, you will have much less overhead compared to our RAID 10 in ACS 4.8. And ACS 4.9 will also support full RoCE transport, NVMe RoCE transport, basically.
Excellent. Do you, Eric, want me to continue to run the next 2 polls?
Yes, I think we're doing great. Can you run the polls, please?
Okay. This is the second poll.
Okay, so let me maybe present this question. So the question is also pretty simple. It's what will be the key drivers, according to you, for NVMe SSD disaggregation and adoption? And we listed a couple of them. You may have different in mind, but first one is to reach performance as NVMe SSD attached. Okay, so performance. Second one is about the cost and the cost benefits. The third one is the ease of integration into existing environments. And then, of course, two way to answer with over and I do not know. So if you want to take 10 seconds to think about it and give your answer.
Okay, now I'm going to share the results.
Okay, so thanks for your answers. So it seems that we agree that these three first parameters are, of course, very important. Then it's a question of how you rank them. But we definitely believe, I think we've got the same view that performance, of course, is important because that's a reason why you accept to pay for the price of NVMe. But one of the key reasons of disaggregation, of course, is cost improvement. But it can only be possible if it's an easy solution to use and easy solution to integrate with existing environments. So I believe that's very much in line with what we believe will be triggering the SSD disaggregation adoption. Maybe shall we go to the next poll?
Move on to the third poll then.
Yeah, the third poll actually seems very similar to the previous one. But from a different angle, okay, which is what are the main roadblocks for NVMe disaggregation? And basically, another way to ask the question is why is this adoption so slow? Because we've been talking about segregation for a long time. So what does it take so much time? And same type of answers, the same answers to select. Either performance issue, either cost issue, either ease of integration issue, or something else.
Here we have the results.
Okay, so this one, I mean, I think it's interesting because even if the answers you could select were different, we see that the results are different. And here, what you emphasize is that the main reason why this technology has not been adopted is ease of integration, right? Okay, which is, I believe, extremely important. That's something that on our side we try definitely to take into consideration, and that's one of the reasons we decide actually to provide turnkey solutions, because we believe that the industry is very excited about these technologies, but don't want to invest in developing complex solutions, integrating complex solutions. So the point on our side is really to focus on making integration as easy and fast as possible, and that's definitely a challenge for the industry. Very interesting. Thank you very much for these answers. So,
question from my side. One question, please.
Yes, please go ahead.
Yeah, if the cost, what's about the infrastructure? Do I need 100 gigabit Ethernet over all the data center, or can I also start with a 40 gigabit infrastructure?
So definitely you can start with a lower bandwidth than 100. So 40, 25, 10 is supported. Okay.
Okay.
And also something which is very important, we do not emphasize, but you may be aware that there is basically two ways to support NVMe fabric, either TCP, either Rocky, right? And we've been focusing in the last few months on TCP, okay? But for the exact reason you asked the question, it's about ease of adoption and price, okay? Even if you've seen that in our roadmap, of course, we do support Rocky, at least. Just a question of launching that. Really the focus today is for ease of integration and cost.
Thank you.
Okay, thank you very much. Okay, so if there is no other question, I suggest that we move to the technical corner. And so we go into more details. I know that most of you are technical expert, or at least you have a lot of interest in the way things work. So let's go into the details. Sebastian?
Yeah, so I will basically give more details about the Flashbox internals. So I think you already got some of this information in the video earlier. So the Flashbox basically has two hot pluggable I/O modules. So it's a fully resilient design that allows to pull out one I/O module without stopping the Flashbox. So the Flashbox also supports two independent power supplies and fans. Each I/O module you can fit in from 1 to 3 K200 LPs, so Kalray cards. Basically, the drives within the Flashbox are dual-ported drives, and they will be available from two cards. The two cards being on two different I/O modules, which allows us to have two different paths to the drive. So basically, this is the high availability architecture that we have put in place. And thanks to that, there is just basically no single point of failure in the hardware of Flashbox. So as we have seen in the Paul, the easiness of integration is really a key point of adopting such products as our Flashbox. So that's why we have really focused on the ease of integration and the support of existing ecosystem, basically. So we already said that we support the integration into most of the orchestrator technologies available on the market. So here you see Kubernetes and OpenStack, but we also support OpenNebula and Xen Next Gen, so XCP NG. So this is for the orchestration. We have some partners integrating our Flashbox inside their storage offer for parallel file system support. So as you can see here, we mention IBM Spectrum Scale and BGFS. So we have two different partners integrating our solution into their storage offer for BGFS and Spectrum Scale support. And we have also developed a web UI to ease the orchestration and configuration of our Flashbox. So it's called Kalray Composer. One key point that is not mentioned here, but that I mentioned before, is the work in progress we have with VMware, so that our Flashbox is listed as a reference component, hardware component compatible with VMware. I think this will also be a key point to, let's say, increase the adoption rate of our product. And let's talk now about the Flashbox versus competition. So here we have some comparison between our Kalray Flashbox on the right with, so this is the 6-card version, so which offers the best performances versus, let's say, a storage vendor solution. So here it's a NetApp solution, basically, that we have compared with. And so in terms of IOPs, the NetApp solution is reaching 2 mega IOPs, whereas our Flashbox product is able to reach 12 mega IOPs in the 6-card version. In terms of bandwidth, we also have very similar speedup compared to the legacy solution, storage vendor solution. So the legacy storage vendor solution is around 44 gigabytes per second, whereas with our Kalray Flashbox, we are able to reach 72 gigabytes per second in the 6-card configuration. As you can see, we also have a very good latency. So the latency will be 20 microseconds in rocky transport mode. And of course, it will be a little bit higher in the TCP transport mode, so 50 microseconds. But in both cases, as you can see, it's much lower than the latency exposed by the storage vendor solution. The key point is that we not only support much better performances, but we also have similar support for storage services. And we, of course, have high availability support, which is a key point in the storage world. So in terms of deployment, the software license is included with our Flashbox. And a key point is that we also offer, we have a SDK offer, which allows some partners to implement their own storage services on top of the one already provided by Kalray. So, sorry, any question? Okay, so let me finish on this slide. So basically, the key point to remember here is that our Flashbox is really reaching an unbeatable IOPs per dollar and IOPs per watt ratio compared to the legacy storage vendor solutions. So let's go back to the Flashbox product characteristics. The chassis itself, so as we already said, it's a chassis from Vikings, which is a well-known ODM and also well-known for the quality of their hardware. So the rack unit is a two units enclosure. It features 2 I/O modules, 6 fans, and 2 power modules. When you, in terms of Ethernet connectivity, it will have between 4 to 12 100 gigabit per second Ethernet ports. So this is depending on the number of K200LP you fit into the chassis. And we have also some 1 gig system management interface, which are basically used to communicate with the BMCs within the chassis. So the chassis supports dual-ported drives, which is a key point to support high availability. In terms of software, the software suite that we deliver is our access core storage delivery. And this is open source SPDK based, as Remy will share more details about that just after. We have a full roadmap that I presented about the storage services that we plan to support. As you have seen in the roadmap, we already support logical volumes and thin provisioning. Snapshots and clones are will be delivered very soon, and then we will add on top of that RAID 10 and RAID 6 this summer. So we have a roadmap of storage services that is coming very soon. We also have this Kalray Composer UI that allows to configure very easily either one Flashbox or a pool of Flashbox. And of course, the Flashbox will be upgradable on the field. So we have reliable firmware update support, of course, so that it's easy to upgrade the Flashbox with newer access core storage deliveries. So let's go into the details of what is a DPU. Here we are really talking about a new class of programmable processors, which are specialized into running data center infrastructure services. So basically, the idea is really that a DPU is able to accelerate either networking functionalities like virtual switching or network address translation, for example. It should also be able to accelerate, of course, storage. So storage acceleration is really efficient when you talk about NVMe over fabric, compression, DDoP, or encryption. And of course, security is also a key point that DPU should support. So it can be for network functions like firewalling, but it can also be for storage about encrypting the data on disks or encrypting the data in motion. For example, NVMe over Fabric TCP as a TLS version, so you can basically encrypt all the storage traffic thanks to that. So all those key features are really the key features a DPU should support to accelerate software-defined data center infrastructure services of the future, basically.
Sebastian?
Yeah.
Sebastian, we have a question in the chat. This is from Michael Matzer. Michael is asking, so if you offer best price performance ratio, what is the price per gigabit per second? There was one slide that stated this, I think. So the price per gigabit per second, please.
Do we have the figure somewhere? I'm not sure I have it in on the top of my head. Could somebody have a look and try to find this information while I'm talking, if you don't mind?
Sure.
Yeah,
thank you.
Yeah, we don't
fantastic.
have
Michael, we will put the answer here on the chat for you.
Thank you very much. So let's go back to the key features of a DPU. So one key point is that the DPU must be fully programmable. And when I say fully programmable, I mean management plane, control plane, and data plane. So of course, the key difficulty is to have a programmable data plane still being able to keep the performances. Then a DPU must have some high performance PCIe interface with support for virtualization, of course. It should also have high performance network interfaces with hardware to support packet parsing, matching, and dispatching the packets within the DPU. And of course, it should support all the usual TCP acceleration offloads like checksums, RSS, or large receive offload, for example. Usually for some of the features, you need some tightly coupled inline accelerators so that you are able to sustain the line rate. So for example, crypto accelerators are usually a key feature of DPUs. Similarly, compression acceleration or erasure coding acceleration for storage are two key features that usually require inline accelerators. And of course, in terms of security, a DPU should support a secure boot with the root of trust. It should also support secure firmware upgrades. Today, the current DPU landscape that we have is, so here on this slide, you see the major actors in the DPU landscape. So you have, of course, NVIDIA was, thanks to the buying of Mellanox, they have a pretty aggressive roadmap. So their latest commercialized product is the Bluefield 2, which is essentially ARM CPU plus the hardware of ConnectX-6 within the same die, basically. Then similarly, you have Broadcom. I think Broadcom has stopped their DPU roadmap, as far as I understood. But basically, they had the Stingray, which similarly to the Bluefield 2 is essentially ARM CPU complex plus some NetExtreme hardware in one die, basically. Marvell is also, let's say, pretty active in the DPU landscape. So they have their Liquid IO 3, which features a pretty big ARM CPU complex, plus some PCIe Gen 4 support and two 100 gig Ethernet interfaces. And of course, you also have on the right, let's say, more startup, or I would say newcomers in this market. So Fungible and Kalray, of course, with quite similar approaches between Fungible and Kalray in terms of hardware architecture. So let's go to the details of the Kalray DPU in next slide. So on the left side, you see the usual approach that we have seen has been used by, let's say, people like NVIDIA or Broadcom. So basically, in their case, what they did is they just used some hardware from their NIC offer, so which is basically the ASIC part on the bottom, and they have added in the same die some ARM CPU complex, basically. So this approach looks more like a kind of quick and dirty approach, basically, just to do with what they had available. But the problem with such approach is that the data plane is fully hardware, and as long as you just use the hardware data plane, you still have very good performances. But as soon as you want to put the CPU cores into the data planes to do some processing, then the performances really collapse. So that's why on the Kalray side, we have decided to use a very different approach. So in our case, the architecture is based on a many core architecture. So our MPPA features features 80 highly efficient VLIW cores. So those cores are gathered into 5 clusters of 16 cores. And thanks to this approach, we are able to have a data plane that will run that is running on 64 of the cores, and thanks to that, we are able to support much better performances even when the cores are doing processing. So we have much more flexibility thanks to this approach than with the legacy approach you see on the left side. Of course, we have some tightly coupled accelerators for crypto acceleration and erasure coding. We also have some AI acceleration coprocessor, which is pretty unique, I think, today in the DPU landscape. We have 2 100 gigabits per second Ethernet interfaces, and PCI Gen 4 by 16 lane interfaces. So as you see, we have all the features to make really a state-of-the-art DPU, especially to address the storage market, basically.
Right. So we have a couple of other questions. So one which Michael asked again, and I'm not sure whether we can give an actual answer. The question is again from Michael Matza. The ratio probably depends on the number of KLP cards in a flash box. Maximum is 6 with 2 gigabits per second per card. Is that correct? So the ratio probably depends on the number of KLP cards in a flash box. Maximum 6 with 2 Gbps per card. Is that correct?
Yes, it is.
Excellent. So Michael, there is your answer. Yes, it is. We then have another question, again from Michael. Is there a table of figures per configuration?
I think we can have that. I don't think we have it under our hand right now.
Okay.
Yeah, but maybe just to complement, I mean, so definitely that's not something that we have in the presentation, but that's easy to provide. But just to make it very simple to calculate, at least in terms of performance, as you understood, it's very flexible. So you can put from 2 to 6 cards, and each card is 2 MIOPs. It gives you a good indication of the type of performance you can get. And then, of course, depending the configuration, the capacity, the price may be different. So that's why providing ratio then, of course, depends a lot about what type of real configuration you want to build.
So it's 2 MIOPs and 12 gigabytes per second per card.
Yeah.
Okay. Another question from another Michael, this time from Michael Eckstein. How do the Kalray compare to the high-end FPGAs/ACAP of, and I'm going to butcher the name, I apologize, Xilinx, especially the Verso ACAPS? And you can find the question in the chat if I completely butchered it. I'm sorry.
I would say today I don't think Xilinx is targeting the storage market with their Versal architecture, or at least we did not find any performance figures about what they would be supporting with their FPGAs.
Yeah, but maybe we can, Sebastian, I think actually you've got the exact slide to answer the question, right? So indeed, maybe, I mean, and I will let you go into the technical details. So you can see, in fact, I think, Michael, that's a good question. You can see that our technology actually is a very good alternative to FPGA-like type of acceleration cards. Okay, and so there are two ways to answer your question. The first one is about, the specific storage use case, and as mentioned, Sebastian, I think we don't see as a competitor today a solution using Xilinx providing a complete storage stack and so on. Okay. Anyway, you're right in the sense that our cards can be compared to Xilinx Versal cards, and you've got in front of you a table which is comparing the technologies. Okay, so comparing our technology that we call DPU here versus FPGA. And maybe, I mean, Sebastian, maybe we should not go into the detail because we're running out of time, but I can just explain very rapidly the main differences. Main differences actually is that first, I mean, FPGA and ACAP type of platform are pretty difficult to program for a couple of reasons. The first one is that FPGA is always very difficult to program. And then the current Xilinx Versal solution is a combination of cores, accelerator, FPGA, which makes it even more complex to program. And second, also big difference here is in terms usually of total cost of the solution. FPGA-based solutions are usually pretty expensive and power consuming versus our solution.
Okay, so bear with me, guys. We've got quite a few questions. So Michael Matzo is asking again. So the Kalray customer needs to calculate for themselves what Flashbox configuration is best for them?
Oh, so actually, it's much simpler. Usually, I mean, we have a chat with our customers, and this also that this can be performed by a reseller. It's very simple. So we try to understand the performance they need, the capacity they need, and because we've got this very flexible approach, then we've got an Excel sheet which provides immediately the level of performance, the kind of best configuration they can get, and the price basically. So it's really easy, very few parameters, but really the beauty of this approach is that you can easily customize it depending on your needs.
Okay, one more question. This is from Hartmut Veer. Are there any analyst papers about the difference between the usual approach and the Kalray approach concerning DPUs? Any analyst papers that we have?
I'm not aware of any analyst paper, but we can at least look at the figures. Basically, if you look at NVMe TCP performance figures, basically, as far as we know, on Bluefield 2, NVIDIA is less than 1 mega IOPS. I think they are supporting 0.7 mega IOPS, something like that, whereas we are able to reach 2 mega IOPS. Well, this really shows that for a protocol like NVMe TCP, where you need software, really our approach is better.
Okay.
And maybe I see that I've seen on the chat the comment. I love Excel sheets and I like it. But I mean, more than welcome. Let's take one configuration if you want. Okay. We can take one configuration which is a 6 card. Okay, so 6 card means 12 MIOPS, okay, 24 SSDs, okay. And if you make the calculation for 12 MIOPS, okay, if you want to just to give you a ballpark figures in terms of price per MIOPS, basically, you can see that for 12 MIOPS, you can have solutions as low as 2K per MIOPS. Okay, so at least give you a concrete figure. Okay, and then of course, once again, the point of Excel sheet, as you said, is not to be secret or whatever. It's more that we offer the flexibility. Okay, so it's really depending on your needs.
Excellent, thank you. Any more questions? Love all the questions, guys. They are brilliant. They're very, very good. No, okay. Sebastian, back to you. Thank you.
Okay, so I think Eric basically commented this slide. So since we are running out of time, I think we can proceed. So basically here you have a diagram that basically compares our DPU-based flashbox solution compared to either x86-based all-flash array or legacy storage vendor solutions in terms of both IOPs per dollar and IOPs per watt. And as you see, we believe our solution has a key competitive advantage versus the two other listed solutions here for those two key criteria.
So Remy, I mean, we are running a little bit out of time, but I think you can rapidly share the key details about the acceleration card and especially explain how open is the acceleration card. I think that would be great, right?
Yeah, I will try to make it fast. Basically, give some details about the acceleration card and the way we program it, and an overview of the software architecture. So as we mentioned, each card is able to provide up to mega IOPs when connected to NVMe-oF fabric. We run most of all the storage services, as we mentioned, RAID, data reduction like deduplication or compression. It's a pretty low power. Something that we did that highlighted is that it's really plug and play, either in a flashbox, but it can also be plugged inside a server. And in this case, we provide NVMe functionality. So this means that any server with the NVMe driver will be able to use the card. And of course, it's fully programmable based on open source SPDK framework. I will go in more detail in next slide. Again, some key figures about the key point about the card itself. So we have some data management using RESTful API. We provide data protection through the RAID services, availability, we mentioned it already. Security, thanks to hardware cryptographic accelerator inside the MPPA, and the storage efficiency by using compression. Concerning the interfaces, twice 100 gigabit Ethernet, PCI Gen 4 by 16, which can behave either in root complex, like in the flashbox. In this case, you don't have any host processor. The card itself is autonomous and can take over the control of the SSD without any host, or it can be plugged inside a host, and in case behave like standard NVMe devices. And we are pretty low power, around 30 watts. And as mentioned, we are compliant with NVMe protocol inside the host. Okay. Now a quick overview of the access core storage software architecture. So the DPU is running all the data service itself, which means that in case we are inside a server, everything can be executed inside the DPU. So we start by basic services like the TCP termination for NVMe TCP, logical volumes, and with synchronizing and snapshot. That's what is currently supported in the current ACS 4.6 release. We will add later on data reduction through compression, deduplication thanks to cryptographic accelerator and zero detection. We also currently providing RAID 0 and RAID 1, and we are working right now for the next mid-year for RAID 6 with a razor coding algorithm. Thanks to our cryptographic accelerator, we are able to provide encryption at rest and encryption in motion using IPsec or TLS acceleration. Quick overview of the software architecture. So as Sébastien mentioned it, our architecture is a many core architecture. we have 80 core organized in clusters. Each cluster is composed with each cluster has 16 core, and this cluster can be considered as a standalone SMP engine, which means that we can have a Linux running on a cluster and light operating system running on other cluster. In this picture, you can see on the right that the Linux part is responsible for the control plane and management plane. This means that we can have any customer application running on this cluster. And on the left, you can see 4 clusters dedicated for the data plane processing. This cluster will run the full NVMe-oF fabric stack and network stack and the port of a SPDK framework in order to provide all the storage services that I mentioned before. Some details about the Linux part. You can see a SPDK application. This SPDK is responsible for control plane mainly, which means enumerating SSD, opening the queues for SSD. We have optionally a way to configure through external API like Redfish, Swordfish also. Next. And on the data plane side, we have some cores inside a cluster. So I will detail a cluster, but imagine that it's replicated 4 times. Inside a cluster, you have some cores dedicated to perform a network stack. The network stack is a third-party optimized stack for our processor and perform TCP IP and RDMA over converged Ethernet termination, and communicate, next slide, with the second part of the NVMe fabric stack, which is a storage stack. The storage stack basically is another SPDK instance running on our light operating system. Remember that on data plane core, we don't have Linux. It's really lightweight operating system. And the storage stack receive IOs coming from the Ethernet. We are able to provide hardware acceleration for erasure coding, compression, and so on. And then we are directly accessing NVMe drives through their dedicated IO queues, which means that, next slide, that we are able to provide Ethernet to SSD pass directly inside the data plane core without any traffic going through the control plane or Linux or complex stack. So as you can see here, we have 80 cores available per card. Everything is fully programmable, including the data path, which is programmable in C, C++ as any processor. And we provide a standard SPDK API for the data plane, which means that any customer willing to provide and to port its own storage services can develop the storage services on the x86 platform and SPDK and really easily port it to the data plane part in our SPDK on the data plane cores. We provide services like RAID 0, RAID 1, RAID 6, any other services that the customer would like to port. We support high availability, logical volume management, SIM provisioning, snapshot, encryption, deduplication, and the list is depending on the customer. We want to include its own services. So the conclusion that it's a really complete and modular software framework based on optimized SPDK for both the data plane and control plane, and it's open to partner through our SDK. And conclusion, the key advantages of SPDK on the optimized mini-core implementation. We are scalable. We have multiple instances of SPDK. As you can understand, there are 5 instances, one for Linux for control plane, and 4 on Light OS for data plane. But from the external world, the configuration only see a single instance. This complexity is hidden by the Linux control plane. This is a really modular block device abstraction layer approach, which means that any block device, which is a storage services, can be fed from the network, but also from the PCI in case we are inside a server through the NVMe emulation. We have a really efficient SPDK on our Light proprietary operating system, which means that it's really optimized for cache utilization, and it doesn't rely on Linux, which may add some CPU load. We are already optimized, and we have a really efficient inter-cluster I/O communication. You can see that we have 4 instances, but the 4 instances of SPDK can communicate each other without any memory copy, because all the memory is seen by every processor. So this means that we can have I/O between instances and perform load balancing, striping between SPDK instances. Okay. So that's it.
Merci Sébastien.
Rémi.
So I have a question about hyperconverged infrastructure and the disaggregating HCI topic that you addressed the last time I heard your presentation. So is this still a good opportunity for your solution, this disaggregation of existing HCI infrastructures? And additional question, when I will do this, do I have to pull out the local storage out of my hyper-converged infrastructure systems, or does I only add a Kalray flashbox to the existing environment?
Okay, so
yep.
I may answer the first one, and maybe Sebastian, you can answer the second one, which is straightforward. But for regarding HCI, what we see today is that definitely, so of course, what we presented definitely apply to HCI infrastructure, definitely. And we see definitely a lot of interest, for the simple reason is that using HCI, if you have NVMe drive and you cut and paste this NVMe drive configuration in each server, keeping in mind that NVMe drives bandwidth and capacity is growing, also in terms of price, then you really have a problem in terms of how do I share the resource and how do I manage in much more flexible and easy way this resource. So even in HCI infrastructure, there is today definitely an interest in disaggregation and using this type of technology. Okay. And regarding the second question, Sebastian, pretty straightforward. Yep. You want to answer?
Concerning the HCI use case, as I mentioned, the card itself can expose as one or several NVMe devices. These are virtual NVMe devices. These virtual NVMe devices can address behind, inside the board, can be logical volumes constricted by several physical volumes that can be located either inside the server itself or external, or a mix of both, which means that we can have storage capacity by using external flashbox, but we can also benefit from transparent disaggregation by addressing SSD from another storage HCI server. So this is pretty flexible. The disaggregation is entirely managed by the card itself and is not visible through the HCI server itself.
Yeah, but how does the HCI software do the erasure coding then? Because they only is aware of their computing nodes, but not of the external NVMe storage when it's presented as local NVMe drives to the server. So is there a mismatch, or do you have an integration with this erasure coding logarithms from the vendors like Nutanix or VMware vSAN? Or I think that could be a bit complicated to get these two things together.
Actually, you just need to disable the erasure coding feature inside the Nutanix, basically, because we are doing it ourselves. So basically, from the perspective of a vSAN or Nutanix, basically you should just configure your storage just as if it's not resilient at all, and basically the resiliency will be handled by our K200 card.
Okay, so sounds a bit strange for me because I think the resiliency is the key part in the core of the, let's be Nutanix or VMware vSAN, that's the core of this whole solution, to have the resiliency also over rack resiliency and so only to put these these complex technology at the side and say, so okay, I'm doing it on my Kalray backend.
Okay, I understand your point. So basically, there are two ways. Either we integrate, we work with Nutanix, for example, if they are interested in offloading erasure coding on our card, and in that case, of course, we need some integration into their software, so that's one solution. The other possibility is basically more to offer hyper-converged storage, but for let's say non-virtualized infrastructure. So basically more for container bare metal infrastructure. So basically, in that case, you don't have a Nutanix or a VMware. It's just you're running some OpenShift or a Cube on your infra, and basically, thanks to our card, you're able to build still a global pool of storage that is of resilient storage that is shared amongst the pods inside the Kubernetes, for example.
Thank you.
Just to be honest, I think we believe more in the second case, actually.
That's clear.
Yeah, definitely. Thank you, Seb.
Eric, do you have any final comments, Eric or Loic or anyone else from Kalray?
Maybe I just want to thank you very much. I think thanks for your time. Thanks for the excellent questions. It was a pleasure to present our company and our product and technology.